The chess club must decide when to meet for a practice. The possible days are Tuesday, Wednesday, or Thursday. The possible times are 3, 4, or 5 p.m. List the sample space. Well, the sample space is just going to be all possible options that we have. So we have Tuesday, we have Wednesday, we have Thursday. Tuesday could be 3, 4, or 5. By the way, this is called a tree diagram. It's us listing all of our possible options separately. So 3, 4, 5 for Wednesday, 3, 4, 5 for Thursday. So listing the sample space means listing all 1, 2, 3, 4, 5, 6, 7, 8, 9 possibilities. So we have Tuesday at 3 p.m. We have Tuesday at 4 p.m. We have Tuesday at 5 p.m. We have Wednesday at 3 p.m. We have Wednesday at 4 p.m. We have Wednesday at 5 p.m. We have Thursday at 3 p.m. We have Thursday at 4 p.m. And you guessed it, Thursday at 5 p.m. So this is our sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9 possible options that this chess club has. A spinner can land on either red, blue, or green. You spin twice. How many possible outcomes exist? Well, one way of looking at this is saying, all right, well, we have red, we have blue, and we have green. And if I spin red, I can get red again, or blue, or green. Or if I spin blue, I can get red, blue, or green. Or if I spin green, I can get red, blue, or green. But common sense says, wait a minute. There's a little thing called the fundamental counting principle. I don't have to list the possible outcomes. I just have to find how many there are. So if you spin it once, you have 3 options. If you spin it again, you have 3 options. So how many total options are there? Well, the fundamental counting principle says multiply those suckers together and you get 9, baby. And we could see what the 9 is. It's red, 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 blue, red, green. Or blue, red, blue, 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 green. Or green, red, green, blue, green, green. Those are my 9 possible options. So that's what you do. That's what you get. Fundamental counting principle. A jewelry store sells gold and platinum rings. Each ring is fitted with a ruby, sapphire, emerald, or diamond gemstone. How many possible outcomes exist? Well, I don't care what the outcomes are. I only care how many there are that exist. So my first event is the fact that there are 2 types of rings, so that's 2 options. My second event is you can have ruby, sapphire, emerald, or diamond. That's 4 options. Now, when you are trying to find the total possible outcomes, you take the first option and the second option and you multiply them together to get you 8 possible options. Now, I don't need to know what they are. I mean, I could list them. Gold ruby, gold sapphire, gold emerald, gold diamond, platinum ruby, platinum sapphire, platinum emerald, platinum diamond. Those are my 8 options, but I just had to find how many there are, and that's the short way of doing it. A magazine contains 14 pages. You open to a random page. The page number is either going to be 3 or 7. State the probability. All right, so I want the probability of finding a 3 or a 7. Now, generally speaking, the probability of an outcome occurring is the amount of possibilities you want over the total possible outcomes. Now, my total possible outcome for this is going to be 14 because there's 14 pages. I want either 3 or 7. That's 2 outcomes that I want. 2 divided by 14 is 1 over 7. So the probability of me turning to randomly 3 or 7 isn't that high, but possible. A box contains 3 red playing cards, numbered 1 to 3. I like pictures. Let's draw it out. Those are my 3 red playing cards labeled 1 through 3. Also, it has 5 black playing cards numbered 1, 2, 3, 4, and 5. All right. You randomly pick a playing card. It is black or has an odd number. State the probability. All right, so we need the probability of getting a, what was it? A black or an odd, or an odd, or an odd. Now, probability, generally speaking, is a fraction. and it's the options that you want over the total possible outcomes. My total possible outcomes are 1, 2, 3, 1, 2, 3, 4, 5, 8. So I'm going to have over 8. Now this is where it gets fun. It could be either black or an odd number. So if I reach in there and a black card pops out, that's 1, 2, 3, 4, 5 possibilities. Or it could be 1 or 3 red. That's a possibility. If it's both black and odd, hooray! Really, the only possibility that won't count is this poor red 2 that's just lingering around. Poor red 2. So the possibilities that I want are 7 of them. So the probability of me reaching in and randomly grabbing a black or odd card is very high with the 7 over 8. Okay, so that's how you do it. Simplify 4 total permutations taken 2 at a time. The general formula for permutations is NPR, like the radio station, and that's going to be n factorial over n minus r factorial. Now, factorial is when you take a number and you multiply the next integer underneath it and make your way down to 1. What we're going to do here is we're going to set up n, which is 4, so 4 factorial, over n minus r, which is 4 minus 2, in parentheses, factorial. So 4 factorial, I won't mess with it yet. 4 minus 2 is 2 over 2 factorial. So to list out 4 factorial, it's going to be 4 times 3 times 2 times 1. To list out 2 factorial, it's 2 times 1. And look at that! Things cancel out. 2's and 1's cancel out, and you're left with just 4 times 3, which is 12. And that's how you do permutations. Total permutations taken are at a time. Find the number of unique permutations of the letters in the word steel. Now, none of these letters are the same. So if you're going to organize, and order does matter for permutations, you're just going to take the total amount of objects that you have and take the factorial of it. So in this case, since steel is made up of 1, 2, 3, 4, 5 letters, 5 factorial is going to be our guy. 5 factorial is you start out with 5 and you work your way down integers until you hit 1, multiplying everything in between. So 5 times 4 times 3 times 2 times 1, which is 5 times 4 is 20, 20 minus 3 is 60, 60 minus 2 is 120, 120 times 1 is also 120. There are 120 ways that you can write out the word steel. Now this makes sense, right? Because if I were to randomly select a letter, there's 5 possibilities. So if I pick T, that leaves me with 4 possibilities to pick the next letter, which leaves me with 3 possibilities. And according to the fundamental counting principle, whenever you're looking for total outcomes, you multiply the numbers in between. So that's why this all makes sense. Find the number of unique permutations of the letters in the word freedom. Now, normally if we're trying to find permutations, we take the total number of objects that we have and we factorial it. Now, in a case like this, I see repeats. If you have any of your objects repeating, what you do is you divide that total factorial by whatever repeats and how many there are. So if we have a letter being repeated 3 times, we would do 3 factorial. And if it happens again, we do it however many times again, and then we keep going until we're done repeating. Now in this case, there's 7 letters in the word freedom. E is used twice. So 7 factorial over 2 factorial is what we're going to set up. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1. The 2 and the 1's cancel each other out because that's how math works. And you are left with 7 times 6 times 5 times 4 times 3, which ends up being 2,520. Now, what this over 2 does is this over 2 counts in the effect that, like, look, if I were to swap this E and that E, like, it's the same word. I'm not going to count that word twice if I swap the E and the E. So, it literally, by doing this, we eliminate half of our options. So, instead of 5,000 something, we have 2,000 something. Okay? And that's how you do it. Simplify 11 combinations taken 8 at a time. The formula for combinations is NCR equals n factorial over r factorial times n minus r factorial. So we know that n is 11, we know that r is 8, and so we are going to find 11 factorial over 8 factorial times 11 minus 8 factorial. Now before I start ripping things apart, 11 factorial over 8 factorial times 3 factorial. Now what's going to happen is after I list out 11 factorial, 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we realize that that 8 factorial is going to kill off almost this whole thing. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then times 3 times 2 times 1. Okay, the 8 factorial kills off most of 11 factorial because you just cross things out. That leaves me with 11 times 10 times 9 over 3 times 2 times 1. 11 times 10 is 111 times, 110, my bad, times 9 is 990. Divide that by 6, and you get 165. And that's how it's done. List all possible combinations of T, V, and W taken 2 at a time. All right, well, let's start out with T. T could be T and V, and T could be T and W. V could be V and T, and V could be V and W, and W could be W and T, and W could be W and V. Now, here's the thing. Combinations doesn't care about order. So TV and VT are the same thing. TW and WT are the same thing. VW and WV are the same thing. So I only have 3 options. TV, TW, and VW. Volkswagen. Anyway, those are your 3 options. All right, you ready for a tricky problem? Castell and Joe are planning trips to 3 different countries this year. There are 7 countries they would like to visit. One trip would be 1 week long, another trip is 2 days long, and the other trip is 2 weeks long. How many possibilities are there? Now, the combination of their 3 different countries from 7 is a combination because the order in which we choose these countries doesn't matter. For example, if I wanted to be like Spain, Mexico, Venezuela, I could do Venezuela, Spain, Mexico, and still get the same exact possible 3 options. So this guy right here is a combination, 7 total combinations taken 3 at a time. What does matter is the duration. So this is where things do matter. So this is a permutation. The one trip will be 1 week long, another 2 days, and another 2 weeks is a permutation. So we are going to multiply this combination to a permutation of 3 factorial. So let's do the combination first. The combination formula is n factorial over r factorial times n minus r factorial. So this is going to be 7 factorial, because you're my n, you're my r, over 3 factorial times 7 minus 3 factorial. Okay? That is going to be 7 factorial over 3 factorial over 4 factorial. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 4 times 3 times 2 times 1. Let's cross out what we can cross out. 3, 2, 1, 3, 2, 1. 4, 4. 3 and 2 is 6. Those cross out. So that leaves us with 7 times 5 over 1, which is just 35. So 7 combinations taken 3 at a time is 35. 3 factorial right here is just 3 times 2 times 1, which is 6. So 35 times 6 is going to be our guy, and 35 times 6 is 21 with a 0 at the end of it, or 210 if you want. So a pretty tricky problem, but a lot of fun. How many possibilities exist if selecting which 9 players will be in the batting, I guess I should say, the batting order or whatever, on an 11-person team? Now, this is a combination. So if I'm like Johnny, Sally, Susie, blah, 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 and I go Sally, Susie, Johnny, it's still the same 9 people. I don't care about the order in which they're batting because it doesn't say I care about the order in which they're batting. So this is a combination where it's 11 people taken 9 at a time. So that formula is n factorial over r factorial times n minus r factorial. You are my n, you are my r. So 11 factorial over 9 factorial times the quantity 11 minus 9 factorial. So that's 11 factorial over 9 factorial times 2 factorial. Okay? 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 9 factorial is going to kill all of that off. So 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then times 2 times 1. So like I said before, that 9 factorial kills off almost all of this stuff up here. They just cross each other out. Okay, so I'm left with 11 times 10, which is 110, over 2 times 1, which is 2, and there's 55 possible options. And you might be thinking, whoa, 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 that doesn't seem like a lot. No, it's not, because the combination doesn't matter. Okay, the order, I mean, doesn't matter. I don't care what 9 kids I pick, what order those kids I pick them. If I'm just going through a list, I'm like, you, that's all that matters. So you're not going to get a huge number if it's a combination. A group of 45 people are going to run a race. The top 3 runners earn gold, silver, and bronze medals. How many possibilities are there? Well, we care about the order in which these people finish. So this is going to be a permutation. So it's going to be a total amount of people. And we have what? Taken 3 at a time. So NPR. Now that's the formula n factorial over n minus r factorial. My n in this case is 45. Since there's gold, silver, bronze, my r is going to be 3. So I have 45 permutations taken 3 at a time. So that's going to be 45 factorial over 45 minus 3 factorial, which is 45 factorial over 42 factorial. Now, the last thing I want to do is write out 45 factorial. That's a lot, so I'm not going to do that. What I'm going to do is I'm going to be smart. I'm going to say 45 times 44 times 43, look at the bottom, times 42 factorial over 42 factorial has the 42 factorials canceling each other out. So I'm left with 45 times 44 times 43, which happens to be 85,140. So lots of options, lots of possibilities. But those are my answers. It's my answer. I'm done. Like and subscribe.